Students, now we will study about magnetic effect of current and magnetism. First of all, students, in 1820, Danish physicist Hans Christian Oersted conducted an experiment, and according to the experiment conducted by the Oersted, when a magnetic needle is placed over the wire is there, current flows through the wire, and magnetic needle is placed on the wire, and the direction of the magnetic needle and the direction of the current is along the same axis. So if current flows through the wire, then he observes that the magnetic needle gets, the north pole of the magnetic needle gets deflected away from the current carrying conductor. So if he observed that when the direction of the current is reversed, then here the current is flowing in this direction. If the direction of the current reversed, then the direction of the deflection of the magnetic needle also change. And the second experiment is when the current passes through this conductor or a wire, and some iron fillings are on the cardboard. Then if current flows through the wire, then the iron fillings forms a concentric circles having center where the current carrying conductor passes through the cardboard. And he observes that the distance between the iron fillings, or you can say the concentric circle, increases when you move from the center towards the edge of this cardboard. So on the basis of these two experiments, he observes that the current carrying conductor produces magnetic effect. So he comes to the conclusion, and the conclusions are: first, there must be a magnetic effect around the current carrying conductor. Remember, students, there must be a magnetic effect. That's why the magnetic needle gets deflected, as well as the iron fillings around the current carrying conductor, they forms a concentric circles. So there must be magnetic effect around the current carrying conductor. Second thing, if I increases, if the current flows through the wire increases, then the deflection of the magnetic needle also increases. It deflects more. So there must be some relation between the current and the magnetic field. Third thing, the nature of the magnetic field is in the form of concentric circle. You have just seen over here, it is in the form of concentric circle, and the direction of the magnetic field is perpendicular to the direction of this current carrying conductor. So these are the three basic conclusions drawn by the Christian Oersted. And now, if the current flows in the direction of the thumb, if this is your right hand, then the fingers represents the direction of the magnetic field, like this. If the current moves like this, magnetic field, it is a region around the current carrying conductor. You have just seen in the Oersted experiment that current carrying conductor develops a region around it in which if you will put any magnetic substance or magnetic needle is placed, that substance or magnetic needle experiences force. So, that particular region is called the magnetic field, or this is also called magnetic flux density. So, this force experienced by the magnetic needle or any magnetic substance is called magnetic force, which can also be represented as Fm, magnetic force. Now, for example, a charge Q plus Q moves in this direction having velocity v, and this charge is moving in the magnetic field having magnetic intensity B, and the two vectors, velocity and the magnetic field, these two are making an angle theta between them. So, remember students, this is very important point. If any charge particles moves in the magnetic field, then the charge particle experiences force. This force experienced by the charge particle is called the magnetic force Fm. And remember, the direction of the force is always perpendicular to the direction of velocity and the magnetic field. So, this can be written as Fm, or you can say magnetic force, which will be Q V vector cross B vector. Remember, this force, magnetic force, is always perpendicular to the plane consisting of velocity and the magnetic field, or you can say Q VB sin theta. This can also be represented like this, where theta is the angle between velocity and the magnetic field. This is also called Fm, magnetic force. Now, we have certain cases related with this. First, in the first case, if theta is 0 or 180 degree, what does it mean? What is the meaning of it? That is, if a charge particle moves along the direction of magnetic field is there and the charge particle is moving along the direction of magnetic field. If theta is 0, then Fm is also 0. So, Fm, magnetic force, is also 0. No force will be experienced by the charge particle. Second condition, if theta is 90 degree, then sin 90 is 1. Therefore, the force, magnetic force, will be QVB. This is the maximum force experienced by the charge particle, which is only possible if charge particle is moving perpendicular to the direction of magnetic field. Magnetic field is like this, charge particle is moving like this, both vectors are at 90 degree. It experiences maximum force, which is perpendicular to the plane consisting of the B and the V, that is like this. So, it is the maximum force. Case 3, if V is equals to 0, that is, if charge particle is at rest in the magnetic field, then if V is equals to 0, magnetic force will also 0, means there will be no magnetic force experienced by the charge particle when the charge particle is at rest. So Fm magnetic force is also 0. Case 4, if theta is equals to 270, if theta is 270 degree, then the force experienced by the charge particle Fm will be minus q Vb. So these are the 4 cases when the charge particle enters in the magnetic field with velocity v. Therefore, the definition of the magnetic field is, you know this formula, magnetic force q v cross b, or this can be modified as q vb sin theta. So this is magnetic force which you studied earlier. Now B can be written as Fm upon qv sin theta. If q is equals to 1 coulomb, v is equals to 1 meter per second, 1 coulomb 1 meter per second, and theta is 90 degree. If you will substitute this condition in this formula, q1 v 1 meter per second, sin 90 1, so B can be written as Fm. What does it mean? If a charge of magnitude 1 coulomb enters in a magnetic field with velocity 1 meter per second and it enters at an angle 90 degree, then whatever be the magnetic force experienced by the charge particle will be numerically equal to the magnetic field intensity. So B if you want to find out the unit of magnetic field intensity, it will be Newton Coulomb meter per second, or this Coulomb per second is also represented as ampere and meter will remain here. Coulomb per second is the unit of current and which is represented by A. So Newton per ampere meter, or this is called Tesla. It is represented by capital T. So Tesla is the SI unit of magnetic field intensity in SI system. In CGS system it is Gauss, and the relation between the two is 1 Gauss is equals to 10 raised to the power minus 4 Tesla. This is the relation between the Gauss and the Tesla. Now we will study about the Lorentz force. This is also very important. When a charge particle having charge Q moves in a region having electric field E and magnetic field B, it experiences a net force called Lorentz force. Both fields are there. You have just studied when a charge particle enters in a magnetic field, how much is the magnetic force experienced? Q V B sin theta. In the first chapter, you studied when a charged particle is placed in the electric field, it also experiences a force. This force is called electric force, which will be Q into E. So, the net force will be F is equals to Fe plus Fm. It is electric force and it is magnetic force. Electric force, according to the first chapter, it is Q into E. As per the definition of electric field intensity, E is equals to F upon Q, force experienced by the charge, so F is equals to EQ. And the magnetic force, just we studied, Q VB sin theta. So, this can be written as Q E plus VB sin theta. This force is called Lorentz force. It is a combination of the force, magnetic force as well as electric force. Now we will study about the magnetic force on the current carrying conductor placed in the uniform magnetic field. For example, this is a current carrying conductor and having length L with area of cross section A. If this current carrying conductor is placed in the magnetic field, let this is the direction of the magnetic field B. The angle between the two is theta. Charged particles, or you can say electrons, are moving in this direction. If electron moves in this direction, then what will be the direction of the current? The current will be in this direction, I. Let this is the small element having length dl. dl is the length of the small element of this current carrying conductor. If this current carrying conductor is placed in the magnetic field, current is flowing through it, it means charges are flowing through it, electrons are flowing through it. So, what is the force experienced by the single electron if it is placed in the magnetic field? This will be represented as Fm, you can say magnetic force, is equals to minus E V cross B. This is the magnetic force experienced by the single electron. Now, what are the total number of electrons present in the small element? According to this expression, particle density N, total number of particles per unit volume, having length L. If you want to find out the total number of particles in the small element dl, so capital N can be written as N into A into dl. So that will be the total number of particles, or you can say electrons, in the small element having length dl. So the total force will be the minus E N A dl, V vector cross B vector. This is the velocity of the electron which moves within the current carrying conductor. And this expression, this is the total number of particles in the small element. If you will multiply it by the single charge, you will get the total charge present in the small. If you will multiply it by the charge, you will get the charge present in the small element dl. Now velocity, it is represented by dl vector upon dt vector cross b vector. Velocity, total length covered by the charged particle with respect to the time, and the current and the direction of the flow of electrons are opposite. Therefore, we prefer minus sign. So, this dq upon dt will be represented as current. Charge flows with respect to time. So, I dl vector cross b vector. This is the magnetic force experienced by the small element having length dl. Therefore, this force will also be represented as a small force for the length dl. Now, if you want to find out the total force experienced by the complete current carrying conductor, you have to integrate this expression, and the complete magnetic force will be I L vector cross B vector. So, this is the total magnetic force experienced by the current carrying conductor. Flows the current I having length L, and it is placed in the magnetic field B. So, if you will remove this cross product, you will get Fm B I L sin theta. Removing cross product, sin theta will comes over here. So, this is the magnetic force experienced. For maximum force experienced by the current carrying conductor, theta should be 90 degree. Therefore, magnetic force and maximum magnetic force, maximum force will be only BIL sin 91. If theta is equals to 0 or 180 degree, then no magnetic force will be experienced by the current carrying conductor. If the direction of the current carrying conductor is along the direction of magnetic field. Next topic is charged particle moving in a uniform magnetic field. Charged particle is moving in a uniform magnetic field. Remember this formula, magnetic force experienced, we just earlier we have studied. It is represented by QVB sin theta. Remember, theta is the angle between the velocity and the magnetic field. Velocity and the magnetic field. Then the charged particle experiences force F. Second thing, just for revision, the magnetic force will always perpendicular to the velocity vector and the magnetic field vector. Now, case 1. If theta is 0, that is, charged particle enters in a magnetic field along the direction of magnetic field. This is the magnetic field having intensity B, and Cross means magnetic lines of forces or magnetic field, you can say, enters into the board. It enters into the board like this. And the charged particle is moving along the direction of magnetic field. This is the direction of the magnetic field, and the charged particle is also moving in the direction of magnetic field. Both are parallel to each other. So, if theta is 0, if you will substitute theta is 0 over here, Fm will be 0. Means no force will be experienced by the charged particle. It goes without deviation. Second case, if theta is equals to 90 degree, it is very important case. That is, this is the direction of magnetic field and charged particle is entering like this. This is the direction of magnetic field. Charged particle enters in this direction like this, in this direction. This is the direction of the velocity, and the charged particle Q enters in the magnetic field. Magnetic field is over here, velocity over here. So, if theta is 90 degree, then the force experienced will be how much? Fm Q V B, or you can write it as Fm Q V vector cross B vector like this. This is the maximum force experienced by the charged particle. Now see the direction. It enters in the magnetic field. Magnetic field is like this. Velocity vector and magnetic field vector both are perpendicular to each other. Both vectors, this vector and this vector. So, the net force, magnetic force experienced by the charged particle will be perpendicular to the both. See, this is the magnetic field, this is the velocity, this will be the force experienced by the charged particle Fm, perpendicular to both. Magnetic field, velocity vector and this magnetic force all are perpendicular to each other. So, this is the direction of velocity vector. Therefore, the two vectors, two vectors are here and both are perpendicular to each other. Therefore, particle will move like this over here. When it comes at the point over here, what will happen? Again, this is the direction of the velocity, this is the direction of the force, and it moved like this. So, this particle moves in a circular form like this. If it comes over here, just you have seen, this is the velocity vector, this is the force experienced by the charged particle towards the inside. So, it forms a circle, that is, charged particle moves in a circle when enters perpendicularly with a velocity v. At every point, this is the velocity vector, this is the magnetic field, this is the magnetic field, this is the velocity. So, force will be experienced perpendicular to the velocity vector and the magnetic field like this. If it comes over here, this is the velocity vector, this is the magnetic field. So, magnetic force will be towards inside. Number 1. So, this magnetic force provides necessary centripetal force to the charged particle, and the centripetal force experienced by the charged particle having mass m, it moves with the velocity v with the radius r. This is expression number 2. So, this centripetal force will be due to the magnetic force when the charged particle enters in a uniform magnetic field. Therefore, mv square upon r q vb. Theta is 90 degree. I have taken over here. So, only the remaining quantity will be q vb. So, by cancelling this velocity from both sides, therefore, the r will be mv upon bq. This is the radius of the charged particle when it enters in the uniform magnetic field. Now, what is the time period of rotation of the charged particle in the magnetic field? Because when it enters from here, it completes one rotation. The total time required by the charged particle will be t is equals to 2 pi r upon velocity. On substituting the value of the radius from this expression, it will be 2 pi upon v into radius mv upon bq. So, this will be 2 pi m upon bq. Time period of the rotation. Expression number 3. Remember this expression, students. This is the time period of rotation of a charged particle. This is independent of radius. It depends upon only the time period of rotation of the charged particle when it enters in the magnetic field, uniform magnetic field. It depends upon the mass, intensity of the field and the charge. It does not depend upon the radius. That is, what is the meaning of it? This is very important term. It is independent of radius. Time period of the rotation of the particle is independent of the radius. Means, if charged particle is moving like this with bigger radius, if charged particle is moving like this with a smaller radius, time period will remain same. What is the conclusion, students? Time period will remain same. Time taken by the charged particle in moving one rotation and this rotation, time period is same. Means what? Velocity increases if the charged particle covers more or bigger radius. Remember this, student. This is very important term, very important line. It is independent of radius. If radius is more, velocity of the charged particle will be also more. Because time period is same, independent to the radius. And the frequency of rotation will be mu is equals to reciprocal of the time period, or this can be written as bq upon 2 pi m. This is frequency of rotation of the charged particle. Now we will study about the third case. If theta is other than 0, 90 degree and 180 degree. It is different from 0, we studied earlier, different from 90 degree, or you can say the charged particle is moving at any angle other than 0, 90 and 180 degree. Then what happens? Now, in case third, if theta is other than 0, 90 degree and 180 degree, different from the above two conditions, or you can say the charged particle is entering at any angle other than 0, 90 and 180 degree, then what happens? See, this is the direction of the magnetic field along x-axis. Charged particle is entering at angle theta degree with velocity b, with this velocity v. Then what happens? Consider the two different components of this velocity vector. This will be the v cos theta and this vector will be the v sin theta. Two components of the velocity vector. V cos theta and the B magnetic field both are in the same direction. This vector and this magnetic field vector both are in the same direction. So, if both are in the same direction, theta is 0. Net force experienced by this velocity component will also 0, as we studied earlier. Theta is 0. So, net force experienced by this vector will also 0. Now, this v sin theta and the magnetic field both are perpendicular to each other. Magnetic field and velocity vector, which component? V sin theta, both are perpendicular to each other. So, it experiences a maximum force, as we studied in this case, second case. So, what will be the magnetic force experienced by the charged particle? It will be Fm will be Q VB sin theta. This is the V sin theta is the component, and this V sin theta is perpendicular to the magnetic field. So, this gives necessary centripetal force, which will be equals to mv square, that is V sin theta whole square upon r. Now, compare the two. So, you can write QVB sin theta is equals to mv sin theta whole square upon r. So, V sin theta will cancel out. So, radius will be how much? Radius will be mv sin theta upon qb. This is the radius of the charged particle when it enters other than the theta 0 or 90 degree. Now, remember this, student. This is mv sin theta upon dq. For calculating the time period, put the value of r, radius of the particle covered within the magnetic field. So, this will be 2 pi into r, mv sin theta upon qv, divided by velocity. Which velocity? Which component of the velocity? It will be the v sin theta. So, v sin theta will be cancelled out. Therefore, the time period will be 2 pi m upon qb. This is the time period of rotation of the particle in the magnetic field. Time period will remain same. Now, very important thing. If the particle moves in the magnetic field, so it moves like this, like this. it will not move in a perfect circle. It will not move in a perfect, it forms like a spiral shaped structure, and the particle moves like this. This is called pitch. The pitch of helix or the spiral shaped, as this charge particle moves not in the perfect circle, but it forms just like a spring like this. So this component of the vector, velocity vector, is which is along the direction of the magnetic field, is v cos theta. Therefore the v cos theta can be written as the linear distance, this is the linear distance covered by the charged particle, upon the time taken in one complete rotation. So the pitch can be written as v cos theta into t, and the time period for complete revolution is 2 pi m upon bq. Therefore the pitch will be written as v cos theta into 2 pi m upon bq. So this is called the linear distance covered during the motion of the particle. So the particle will not move in a perfect circle, but it moves just like a helix or a spring. Some linear distance will be covered, and this linear distance covered will be v cos theta 2 pi m upon bq. This is also called pitch. Now students, we will study about cyclotron. So cyclotron, it is a very important topic. It is a device used to accelerate positive charged particles. First of all, positively charged particles are used to accelerate, like proton, alpha particle, or any positively charged ion. Now what is the principle? When a positively charged particle moves in a high frequency electric field, when both type of fields are there, electric field and magnetic field, high frequency electric field and magnetic field is there, then the particle accelerate. Now what is the construction? See the construction first. It has two Ds, hollow metallic Ds. This is two Ds, it is D1 and it is D2. Both are kept parallel, and one D is like this. This is the upper surface, this is the lower surface, and hollow is there. It is not a complete solid. This is one D, it is another D. So these are two hollow Ds. These two Ds, this is one D, this is another D. On the top and bottom, magnetic field, high magnetic field, north and south poles are there. So magnetic field will be perpendicular to the two Ds. If this is one D, it is another D, magnetic field is just perpendicular to the Ds. So these two Ds now connected with the high frequency oscillator. That is, oscillator means what does this oscillator do? The polarity of the two Ds will change as per the frequency of the oscillator. So this is the construction of the cyclotron. Now how it works? We will use a source charge over here, any positive charge, positively charged ion also. Here it is placed. First of all, this positively charged ion, if it is there, this becomes negative and this becomes positive with the help of oscillator. So if this becomes negative, this positively charged particle will attract towards the d2, and when it enters in the hollow surface, due to the shielding there will be no electric field, only magnetic field is there. From the top there will be only magnetic field. Charged particle enters towards the d2 like this, magnetic field is at the top. So what it will do, it will rotate like this, as you have seen just in the previous topic. When a charged particle enters in the magnetic field perpendicularly, it rotates. So this charged particle rotate like this. As it comes over here, the polarity of the two D's will reverse. It becomes negative and this becomes positive. So if this D1 becomes negative, the charged particle gets attracted towards the D1. As it enters in the D1, again from the top magnetic field is there, so it rotates like this. And again the polarity of the two D's changes. It becomes negative, it becomes positive. So it gets, the positively charged particle gets attracted towards the negatively charged D like this. And if it enter perpendicularly in the magnetic field of the D2, then it rotates like this. So if this process continues like this, and at the last when the particle moves from D1 to D2, so it will comes out from the two D's. Now very important thing, as you studied earlier, that when a charged particle enters in a magnetic field perpendicularly, the time period is independent to the radius of rotation. So whatever be the time required over here in this path, the time period will remain same. If time will remain same, what does it mean? The time required will be same in each path, means the velocity will continuously increase. Velocity of the particle over here, it will be more than this because time period is to be same. And at the last, radius will be maximum, the distance covered by the particle is maximum, so time period will remain same. What does it mean? Velocity will continuously increase, or you can say the particle gets accelerated. So how can you write the working? If particle moves in a magnetic field of D2, because the particle, positively charged particle, gets attracted in the D2. As it attracts from the top, magnetic field is there, both are perpendicular, so it rotates. Therefore the magnetic force experienced by the charged particle will be QVB. Theta is 90 degree, sin theta will be 1. This is the maximum force, number 1. Number 2, this force provides necessary centripetal force. So F will be mv square upon r. Therefore you can write mv square upon r is equals to QVB. This will cancel out. So r is equals to mv upon QV. This is the radius. Now time period of rotation, as you studied earlier. So time period will be time period in one rotation, in half rotation here, time period in half rotation, not in complete rotation. Let the time taken to move the particle in 1D, it is represented by small t. It will be the 2 pi r, it will be pi r upon v. Why pi r? Because we are considering only the 1/2 like this. This is 2 pi r. We don't require 2 pi r because we are calculating only the distance covered in the 1D. It will be the pi r. So, the time taken will be the pi, r will be the mv upon qb and v. Therefore, it will be pi m upon q. This is the time taken by the particle to move in a 1D, and the total time required will be the 2 into t. So, it will be the 2 pi m upon qb. This is the total time required. Frequency of rotation. The frequency of rotation will be mu is equals to, which will be 1 upon t, that will be the qb upon 2 pi m. This is frequency of the rotation. And remember this, if frequency of rotation, if it is equal to the frequency of the oscillator, because this is the frequency of the rotation of the particle inside a cyclotron. If this rotation become equal to the frequency of the oscillator, because the particle is moving from one D to another D according to the frequency of the oscillator. So, when the frequency of the particle becomes equal to the frequency of the oscillator, then this condition is called the resonance condition of a cyclotron. So, remember the resonance condition. If mu is equal to the frequency of oscillator, then this mu will be resonance frequency of a cyclotron. What is the energy gained by the particle? Because we studied here in the very beginning that as the particle radius increases continuously, the time period will remain same and the velocity will increase continuously. So, the maximum energy of the particle will over here when radius is maximum. So, here this is BQV is equals to mv square upon r. This is the force experienced, this is the centripetal force. So, this is the velocity. So, energy of the particle will be half mv square. So, half mv square. Put the value of v over here. So, it will be b square q square r square upon m square, or you can say it will be the half b square q square upon m square into r square. This is the energy of the particle. Now, B, it is a constant magnetic field applied from the top. Q, the charged particle you have taken and it is fixed during a particular experiment. Mass of the particle, it is also fixed. So, this complete thing is a constant. That means that on increasing the radius, if the radius increases, see, If the radius increases, energy of the particle also increases. So, if at the last, when the R is maximum, if R maximum is there, so E maximum will be half B square Q square upon M square into R maximum whole square. So, E maximum will be only possible if the radius of the particle or the positively charged particle is maximum. So, for that orbit, energy of the particle will be maximum. This cyclotron is used to accelerate. Now, there are certain limitations also. What are the limitations? First, cyclotron cannot be used to accelerate for uncharged particles. Uncharged particle, because you know the magnetic force Q V B sin theta. So, charge must be there. Therefore, uncharged particle will not experience any type of magnetic force. Second, it cannot accelerate electrons. Electron will not be accelerated because due to the reason the mass of the electron is very less in comparison to the positively charged ions. Therefore, it attains the maximum velocity in a very few time. So, therefore, electrons cannot be accelerated due to less mass of electrons. Third, the velocity of the positive charged particle cannot be increased continuously, as it is not possible that you can increase the velocity continuously, because the reason is relativistic mass m is equals to m naught under root of 1 minus v square upon c square. What does it mean? If the particle moves with a velocity v, where m naught is the rest mass, then the mass of the particle is m. If v is equals to c, that is, if particle moves with the velocity of light, then what does it mean? This is 1, this will be 0, so mass becomes infinite. That is, mass of the particle increases with the increase in the velocity. Therefore, the velocity cannot be increased continuously, because due to the reason that mass will also increase. So, we cannot increase the energy of the positively charged particle more than 20 million electron volt. Remember. So, these are the few limitations of the cyclotron. Now, there are many uses of cyclotron. Cyclotron is used for various nuclear reactions, because when this particle comes out from the D, it has maximum acceleration, velocity will be maximum, radius is maximum, you studied earlier, energy is maximum for the last orbit, for the last path, and this particle, when it comes out from the cyclotron, it has maximum energy. So, it is used for nuclear reaction for the bombardment. Secondly, this accelerated particle is also used for developing various types of radioactive medicines, and radioactive medicines are used in various therapies. So, these are some uses of cyclotron.